Hello, everyone. My name is Zhang. So I'm here to present my work, Icon Drone Autonomous Indoor Exploration using Unmanned Aerial Vehicle for Semantic 3D Reconstructions, which I did with my partner Yilin, who is not able to make it here today, and also my professor Zhengbo, who's now at Columbia University. So we frame our problem to basically a scan-to-BIM problem. So for people who doesn't know about what a BIM is, it's called Building Information Modeling. It's like a modeling tool that's already been widely adopted in architectural and civil engineering for designing and constructing buildings. So yeah, so after the building is being built, so past research has also tried to use this models for, let's say, like a digital twin kind of like applications for simulations, automations, and optimizations to reduce the let's say the carbon activities during the operational stage. However, we find some challenges during doing that. By doing that, first, we have limited resources and fundings for facility management of buildings in operational stage. And also that for many of the older buildings, they just simply don't have BIM. They were constructed using like CAD drawings or just handcrafted drawings, things like that, which brings to the topics of scan-to-BIM. So scan-to-BIM is the major methods for creating BIM models for buildings that are already being built without the BIM. So there are 3 steps identified by previous literatures. So the first step is data acquisitions and pre-processings. That basically means capturing the geometries of the building, let's say a point cloud of the building. And the second part is semantic segmentation of the 3D data. So the data you collected is just raw 3D point clouds, a bunch of points with no meanings. So you want to identify different parts of the point cloud, let's say the ceilings, walls, and floors for buildings applications. And lastly, we'll be developing a 3D models of actually a BIM instead of point clouds. So our work, which leads to our research question. Our research question is that we want to use a robots to click generate a BIM instead of like manually doing everything. So for this work we're presenting, we focus on the first 2 steps. However, we're also implementing the 3rd step as well. So the first 2 steps is data acquisitions and also semantic labelings. Yeah, here is our drones, which we DIY'd. So yeah, it's a drone that enables fully autonomous indoor explorations and also generating 3D semantic labelings. Here's the picture. And here is the full pipeline. Yeah, so our drone can autonomously navigate and explore the whatever areas you're interested in and generate a 3D point cloud based on video footage. And also we'll use like AI to provide the semantic labelings. And for this work, we're interested in the building materials and also the building components, which we can use to generate our BIM models at the end. Yeah, here is the mechatronic designs of our pipeline of our drones. So in the big picture, we can divide it into 2 parts. So on the left here is the flight controller module, which basically control the postures and how the drone moves, like in the low-level controls. On the right side, on a onboard computer, is the high-level controls, which you can think about it as like the brains of a human. So let's say, put it in the analogy of you want to explore this like great hotel. So there's 2 things you need to know. So the first one is where you are right now, so you know where your position is right now. And the second thing is where's the next location you want to go. So there's like these 2 colored modules that enables you to note where is your like the state of the drones. So for localization, since we're in a indoor setting, so there will be no GPS available, which you be commonly used in commercialized drones, which you guys may already been played with. So yeah, so in this case, we'll be using a visual inertial odometries to localize your drone, so know where your drone is at the moment. So the brief description of this is that giving a image sequence and a IMU measurements of 2 consecutive image frames that observing very similar image features. There's like a math you can do to basically like project the previous frames onto the current frame. And then there's like this transformations you can calculate to know the positions between the 2 camera frames. So by doing that to all the camera frames, you know like a trajectory basically of your of all the different image frames, so that there will be a trajectory of the drones, and there will be tightly coupled. There will be a tightly coupled optimization problems together with the IMUs to get your positions of the drone. Next, after knowing where you are, the next question is where to go next. So we use a hierarchical frontier-based exploration algorithm. So in the nutshell, so basically the drones will be perceiving the space using a depth cameras and using a depth camera, and it will be constructing a 3D voxel grid map in the computer. So for better visualization, we use a 2D one here. So the white boxes are the free space which your drones are allowed to move in, and the red boxes, the red areas, and the black boxes are the obstacles detected by your depth camera, and the gray areas are unknown areas, which is out of sight of your depth cameras. So you can see all those colored boxes. Those are what we call frontiers. Like those are areas between the unknown areas and your free areas. So that's like the places you want to move towards, so you can get into the unknown areas to explore the whole areas. So in the nutshell, so your goal is to move towards the frontier area, so you can explore the whole area of interest. Yeah, if you want more details, please read the paper. Again, for 3D constructions, yeah, it's too hard to get into. So in a nutshell, is that the input will be a video sequence, and the output is a dense 3D point cloud. We're using a multi-view stereo method. So for more details, please go to the paper. Thank you. Yeah, we'll put a little bit more time in the segmentation models. So to train AI models for segmentation, so we'll be using some data sets, apparently. So for building materials, we collected our own data sets, which is about 1,000 images with 12 classes. And for building components, we use a public large data set called ADE20K, which have over 20,000 images with 150 classes. And yeah, given that we are testing our pipeline in with limited resources, we didn't use all the classes listed in the data sets. So these are some of the classes we picked out for evaluations of our pipeline. Yeah, for segmentation model, we just use a very standard swing transformer, so there's not much to talk about here. Yeah, for the fun stuff, here is a demo of our drone flying in a very cluster space. Yeah, so on the far right there is like the 3D voxel grid map that our drone is reconstructing for navigations. So you can see the red things, the red lines is the trajectory of the drone. So it actually can avoid all the obstacles and yeah, trying to explore the designated area as much as possible. Yep. Yep, and here is the reconstruction results and also the exploration path. Yeah, for this one, it was added last minute during shepherding, so we didn't do a lot of extensive experience with it. So here we get to the analysis, which we did in 3 different scenes. So in a classroom, in a lobby area, and also a student lounge. So here is the exploration path of the drones. And yeah, and the reconstruction results, and on the below is the ground truth we collected using a really expensive terrestrial LiDAR scanners. So qualitatively, we compare it, it looks quite similar. The reconstruction results are not too bad. And qualitatively, here are the numbers down there. We compute the cloud-to-cloud distance between our reconstruction and the ground truth. And we have the mean distance down there and the standard deviations. So for these graphs over here, the warmer colors represents larger deviations. So basically, blues are the perfectly reconstructed areas. You can say that way. And yeah, all the other greenish colors are some deviations that detected. So it's not very perfect. So it comes from some errors during the reconstruction from the algorithm. Yep, for the semantic segmentations, here are some of the numbers. You can first look at the overall accuracies down at the very below. So those number tells you like out of the totals, how many pixels or how many points are correctly reconstructed. Yeah, you can see that most of the points are being correctly constructed. But however, if you look into smaller classes, let's say the windows, it didn't do a good job because it was because of the and also the glasses materials. So those two things are components that demonstrates a harder, more diverse behavior that's harder for algorithms to detect. Yeah, here are the qualitative results. So yeah, you can see that most of the points are constructed, labeled correctly using our algorithm. Yep, same for building materials. And to conclude, here are some limitations and future works that we identified. So first of all, the current morphology of our robots cannot access confined spaces. Let's say one of the rooms is fully locked and there's no space, no doors or anything we can sneak our the drone in. So the drone will not be able to explore that areas because it was locked. Or let's say from this room get to the ceiling. So that's not possible right now. And also, we are only tested in very limited scenes. There's no proof our generalizability of these methods right now. Yeah, we aim to do that in the future. So yeah, for the future works, first we would like to reduce the size and weights of the drones for more challenging environments. Let's say the ceilings to reconstruct all the, let's say, the extract components, which is more valuable for folks here, I guess. Yeah, and also to equip more sensors to adapt to different building applications. So just for examples, like we can have a thermal sensors to have the drones navigating around to collect thermal comfort related data. And also we would like to investigate human robot collaborations or multi-robot collaborations. So it can, let's say, address problems like unable to access confined spaces or just open up more possibilities to other tasks as well. So yeah, we'll say that this is not a perfect ready to deploy systems, but it does open up a lot of different opportunities that we are very keen to explore in the very future. Yeah, thank you very much. That will be the presentation.
Okay, questions?
Hello.
Hello.
Yeah. Myself Praveen. I'm from Indian Institute of Science, Bangalore. So great presentation. Congratulations.
Thank you.
And my question is that you mentioned this is a GPS absent environment.
Yep.
So when you are planning your drone from point one to like exploring the environment, So are you going to define any predefined map for exploring, or it's just randomly exploring the environment?
Yeah, so our system is targeted in a like completely unknown areas, let's say buildings without any maps or anything. So it will be exploring fully like on its own. So no prior knowledge at all of the environment.
One more, you have defined some 12 classes for semantic segmentation. So if there is any dynamic obstacle comes, if some person is walking or somewhere, whether it is going to segment that particular object or it will just ignores that one. Any idea?
Sorry, can you repeat the question?
Currently we're segmenting the static environment. If some dynamic obstacle or something comes in between in that point of like field of view, is there going to segment that particular like whatever the object, or it will completely ignores, and whatever the predefined class, those only it will do the segmentation?
Excellent question. So yeah, for the current things, current work presented, we cannot deal with any dynamic objects. So what you see is what you see. So, but yeah, we definitely like I'm working on like right now on a dynamic perception kind of module. So it will like filter out any of the dynamic objects. Let's say people's for say. Yeah, and yeah, that's definitely worth investigating. Yeah.
One last question.
Yeah.
Like you used Swin transformer here in this whatever the architecture
Yeah.
you mentioned. Like why Swin rather than ULO or some other RCNN or something like that?
Oh yeah, we use Wind because it's like just because if it is the SOTA model for segmentation. I know there's like more things coming up like Swing Transformer is from 2022, but yeah, Swing Transformer does the job, and we actually did use like a CNN based methods, which we didn't present here since it doesn't give the same performance as a Swing transformer. So yeah, and this is not a like just like on the segmentation methods so paper. So we didn't include like a whole lot of comparisons between different segmentation models. We just need to prove that our pipeline works. So yeah.
Thank you.
But we did use like a CNN methods. Yeah.
Maybe one more question. Okay, I have a small question. So, can it identify different lighting systems and other like minute fixtures in the buildings?
Excuse me, can you?
Any other like electrical system can it identify?
Oh yeah, great question. So it depends on the segmentation models. I would say, yeah, we didn't do that right now, but of course, yeah. Let's say we can have the drones, let's say navigating in a very confined spaces. We can get to the more extract systems related kind of space. Since yeah, because like out here the electrical systems in this general area is limited for like let's say buildings for let's say the buildings tasks. So yeah, we plan on doing that very soon.
And then the final question. So, have you compared the reconstruction of your images with the actual BIM model and see how much they are overlapping? Because you have BIM model, it's a comprehensive model, right? You'll have a lot of information about all the systems in a building, right? So you compare the output with the actual BIM model from the same building.
Yeah. Oh, like comparing the BIM model we constructed with the actual BIM models, right? Yeah. So we're getting to the last step of generating the BIM models. So we haven't get to that yet. Like I'm doing that right now. So yeah, it will be. Stay tuned. We'll be like maybe releasing that publishing that very soon. So yeah, stay tuned. Thank you.
Okay, thank you. So let's thank the speaker again.